So section 5.6, we want to work with the real zeros of a polynomial function. Now remember, real zeros mean real numbers. Real numbers are anything that looks like a whole number or a positive or negative whole number, fractions, decimals, and also things involving the radical, which we call irrational numbers. So we'll be looking for those types of zeros. The first type of zero we really want to deal with is what's called a rational zero. A rational zero is going to be something that can be expressed as a whole number or integer or fraction or decimal. They're going to be excluding the radicals, the irrational values. So let's see what question 1 deals with to start with. So use the remainder theorem to find the remainder of f of x when f of x is divided by x minus 1. Then use the factor theorem to determine whether x minus 1 is a factor of f of x. So some things to pick up on is this. If a function is divided by x minus r, then f of r represents the remainder. So we have some neat little formula. This happens to be some stuff done by a great mathematician. His name is Rene Descartes. I think that's how you spell it. He does a lot of this here. I think it's like 17th century math is where this comes from. So back in the 1600s and 1700s is where a lot of this was actually developed. So if you want to look at some of the history of math, this is an area that's really cool. Is some of these mathematicians of the time in the 17th and 18th centuries of all the discoveries they made mathematically that now we apply in our own century, the 21st century. So we have this cool little remainder formula, f of r equals the remainder. The catch is, if f of r is equal to 0, then x minus r is also called a factor. So this is the remainder theorem, and this is described as the factor theorem. So if I want to find the remainder of this, instead of dividing using long division on this, instead of actually dividing it by x minus 1, we actually can evaluate if we have x minus 1, then notice that r is actually going to be 1. So if we evaluate f of 1, that will tell us what the actual remainder is if I did long division on this. So 2 to the 1, 2 times 1 to the third minus 6 times 1 squared plus 11 times 1 minus 4. So, 1 cubed is just 1. 2 times 1 is just 2. 1 squared is 1. 6 times 1 is just 6. 11 times 1 is 11. And then we have this minus 4. So what I'm seeing is 2 plus 11 is 13. A negative 6 and a negative 4 is a negative 10. 13 take away 10 would be just 3. So we would be saying that the remainder is 3. So is x minus 1 a factor? Well, since the remainder was not 0, x minus 1 is not a factor. If I want to double check myself, I could type in then 2 in parentheses, 1 close parenthesis, and then up arrow 3, come down, and then minus 6 in parentheses, 1 close parenthesis squared plus 11 times 1 minus 4. And we should get 3. So we do. So it does check out there. So that's how we would apply the remainder theorem, and the factor theorem is it actually allows us to be doing what we've been doing. So we input 1 into the function, and this allows us to not have to worry about using long division. Now, if I did want to use long division, what this looks like is x minus 1 has to go into the function 2x cubed minus 6x squared plus 11x minus 4. So when you do this, make sure your degrees count down 3, 2, 1, 0. That works just fine. So remember, when we do this, we kind of use the front end. How does x minus 1 go into 2x cubed to start with? We just use the front end. Just focus on the x. What times x is going to be 2x cubed? Well, I would need a 2x there. Actually, a 2x squared. 2x squared times x would be 2x cubed, so that works. So then we multiply the 2x squared times the x, so that gives me 2x cubed. And then we multiply 2x squared times a -1, and that's going to be a minus 2x squared. Now, instead of subtracting, the easiest way to do it is just change the signs and add. So this will turn into a negative, and this will turn into a positive. And then we actually add this and bring it down. So this becomes then zeros out, and a -6x squared and a 2x squared is going to be a -4x squared. And then the 11x comes down, and we don't have to worry about bringing the next part down just yet. So then we start this all over again. Just focus on the front end. X goes into -4x squared. In other words, what times x gives me -4x squared? What times x gives me -4x squared would be, looks like a -4x. So if I put a -4x up here, then I have to multiply this -4x times x. So -4x times x would be -4x squared. -4x times -1 would be a positive 4x. Now, again, we're supposed to subtract this, but instead of subtracting, we can change the signs and actually add. So when I add, this is going to become then zeroed out, and 11x and a -4x is going to give me a 7x. And then this minus 4 comes down. And then we do it again. We divide the x minus 1 into this. In other words, what times x minus 1 gives me 7x minus 4? Or in other words, what times x gives me the front end, which is 7x? Well, I would need a 7. So if I put a plus 7 up here, well, 7 times x is going to be 7x. 7 times -1 is a -7. So again, when we subtract, we just change the signs and add. So the -7x, -7x will divide out. -4 plus 7 would be a remainder of 3. Notice how this is now too small, because I can't multiply x by anything that's going to give me 3x, so this is going to be called the leftovers. So we have this remainder of 3. So since there's remainder 3, x minus 1 is not a factor of the polynomial function 2x cubed minus 6x squared plus 11x minus 4. So you can kind of see where we want to avoid long division, and that's where this remainder theorem and factor theorem really help us out with saving some time. Kind of cool.